Hello everyone, my name is Ms. Arya Janhel. I am very honored to participate this year's International Conference on the Energy Storage Technology and Applications, ISETA 2021. Today I will present an electrochemical performance of water-based lithium iron phosphate cathode for lithium-ion batteries. I would like to begin with the problem with current battery technology. My objective is to improve cost and environmental impacts of battery production. I will then discuss the cathode material used for my research and the methodology for my experiment. I will conclude with a discussion of the result. Lithium-ion batteries are the most popular type of rechargeable battery for consumer electronics. They can be used for a variety of products, from mobile phones to cars. In this research project, I focus on the development of the cathode production using lithium iron phosphate as a main raw materials. In cathode production, the commonly used material is polyvinyl leading fluoride or PVDF as a binder, and N-methyl 2-pyridone or NMP as a solvent. These components are expensive, toxic, and affect the environment. To reduce these disadvantages, I therefore study the production of cathode using water as a solvent. The objective to study the cathode electrode using a water-based solution to reduce the production cost and improve environmental friendliness, to find a suitable electrode formulation to get a high-performance battery with 90% LFP using a water-based cathode that has the same capability of the cathode and electrochemical performance of current lithium-ion battery cells. This study will use water as a solvent with following components: 90% lithium-ion batteries with 10% conductive and binders. Lithium iron phosphate can provide high energy and is a very safe and secure technology, all while having a low toxic impact on the environment with long-term stability, and still have some disadvantages such as low electrical conductivity. Graphite or KS6 has very stable conductivity, high efficiency, easy to disperse, easy to grind, corrosion resistance, and improved life cycle rate. Acetylene black or AB has high purity with a carbon content over 99%, has an absorptive power of liquid, excellent electrical conductivity. Carboxymethyl cellulose or CMC is a water-soluble with the property to increase thickness and improve viscosity. Styrene butadiene rubber or SBR helps flexibility, strengthen vital force, and increase heat resistance. My methodology was to make the active material a 90% LFP. This is the main component of the cathode. This is required to achieve a high battery capacity. KS6 and AB are added in the equal parts as the conductive. Because AB is a very pure carbon made at relative high cost, we therefore combine with a KS6 to help reduce production costs. SBR is added at a 2:1 ratio with a CMC as a binder because CMC helps with thickness and viscosity. CMC must be combined with SBR to help in the dispersion and make the electrode more flexible. The experimental process starts with preparing the substance by washing out the material at the correct ratios. Next, with a mixer, I start by combining CMC with a water for 1 hour, then add LFP, AB, and KS6 and mix for 1.5 hours. Then lastly, add the SBR and mix for 1 hour. The cathode production using NMP had the same active and conductive materials, but used the different binder PVDF. The slurry then placed on the aluminum sheets using a vacuum coating machine coated to a thickness of 150 to 200 micron. The sheet is then dried in the vacuum oven, then removed from the oven to coating the another side in the same slurry. This will compress the electrode. Then store compressed electrode in the vacuum oven to wait for assembly the battery cell and test. Next is assembly of the battery cylinder cell and finally to do a test with battery testing machine. Analysis and testing of the experiment will provide general information because of the limited test equipment in the laboratory. Testability of the LiFePO4 cathode is performed by a visual inspection of the external surface and noting about the absorption of the coating. Testing of the lithium-ion battery cylinder cell for electrochemical performance is done with the battery testing machine and then recording the following data about the charge, discharge, voltage, efficiency, and discharge specific capacity of each of battery cell. Part 1 of the study to demonstrate the effect of battery performance when the ratio of conductive and binder is altered. A total of 5 batteries with different ratio were tested. The ratio of conductive to binder were as follows: formula A to E: A 2 to 1, B 1.5 to 1, C 1 to 1, D 1 to 1.5, and E 1 to 2. To find a mode of conductive and binder that produce the best of battery performance. The experimental formula are shown in the table 1. I expect that the right amount of conductive and binder will affect the performance of battery. Talking the formula that give the best result, I will move on to the second part of the study. This slide shows observation of capability of LiFePO4 cathode using different ratio of conductive to binder. The external characteristic of the surface coating of formula A to E were recorded and noted. The pictures were taken with the phone camera, which may not show enough detail like microscope inspection would. Formula A with a lead amount of binder has slightly cracked on the surface. The yellow circle indicates where to clearly to see crack. Formula B and C coating surface of the electrode is good. D had a slightly rough on the surface. The problem could have occurred because the LiFePO4 powder used come from different lot and that was used with A, B, C, formula E with the highest amount of binder. As the previous slides show that when a higher ratio of conductive is used with a low ratio of binder, adhesion is compromised. As is known about the binder help to disperse and improve adhesion of the slurry to aluminum sheets. When binder ratio is too low, the resulting slurry will have issue with the adhesion and cracking of the cathode. Therefore, my findings show that you should not use a conductive to ratio 2 times higher than that of the binder. The information of formula A to E after testing battery cell are as follows. Figure 1 is a voltage and specific capacity of formula A to E when battery cells were charged and discharged. Formula B has the optimum ratio of conductive to binder of 1.5 to 1 and a high discharge specific capacity of the 120 mA per gram. The formula with the next-best discharge specific capacity were C, E, A, and D, respectively. Recall casting result of formula A has cracking because of minimum binder use with a higher ratio of conductive use. It should be resolved in a high specific capacity, but with too high conductive volume, it will be resolved in the insufficient mixing and cracking. It can be inferred that the ratio of conductive to binder affects casting and electrochemical performance of battery lithium. Formula B it seems to have the better ratio of the conductive and binder for adhesion and electrochemical performance. Second part is a comparative study of battery performance between water-based cathode and NMP-based cathode. I will be using the formula B, the best performing formula from first study, for comparison experiment in the part 2 of the study. Table 3 shows the ratio of component for water-based cathode and NMP-based cathode. Continuing with the comparative study, I noticed the mixing time very greatly between the water-based slurry and NMP-based slurry, with NMP-based mixing much quicker. I also found that the cathode surface coating between water-based and NMP-based has slightly different surface characteristics. The both water-based and NMP-based mixture has good adhesion and smoothness, but NMP-based mixture has slightly smoother appearance than. The voltage and specific capacity data is graph for formula water-based and NMP-based, shown in figure 2. When the battery cells were charged and discharged, the NMP-based formula has a higher discharge specific capacity at the 145.4 mAh per gram. The water-based formula come in at the comparative 120 mAh per gram, making it worthy of more study and experimental as more environmentally friendly and cost prohibitive alternative to NMP-based batteries. In conclusion, this study showed that production of the 90% LiFePO battery using a water-based formula for its cathodes can repeat the NMP-based battery to reduce the production cost and improve environmental friendliness. Formula B has shown to be the best formula test with a 1.5 to 1 conductive to binder ratio respectively. Has a very good castability of the LiFePO cathode and repeatable specific capacity of the 120 mAh per gram compared to the industry standard specific capacity of 170 mAh per gram. It has been found that cathode electrode can be produced by using water as a solvent with an efficiency within acceptable level. That brings the presentation to the end. Thank you for your attention.